going to go ahead and take a look at the chi-squared goodness of fit test. Um, it's a use of the chi-squared distribution, and it's used to determine uh, if a current or if a given distribution is accurate. The name of the test is actually really nice. It gives you a good feel for what you're actually going to do with it. Although not grammatically correct, it is asking you how well does the data fit like an expected count or expected proportion. So again, we're going to use a chi-squared distribution. There's just a couple things about the chi-squared distribution. It's skewed right, and uh, when we're going to use it, we're going to base it on n minus 1 degrees of freedom, where n is the number of categories. So just as before, this is still your p-value, is the area that you shaded under the curve. And that cutoff value, instead of, right, with the z-test, we used z-scores and t-distributions with t-tests and t-intervals. This time it's a chi-squared distribution, so this cutoff value, that's kind of small. It's actually going to be a chi-squared value. One thing to notice, this will always be a one-tailed test. You can see it'll always shade up. The hypotheses for a goodness of fit test. The null hypothesis is that the distribution is as stated. So they might say, like a bag of M&Ms, 20% are this color, 18% of this color, 25% of this color. So when you buy a bag of M&Ms, you kind of assume, well, the bag that I just bought is, exactly as stated on the bag. If all of a sudden something seems off about your bag, you might run a chi-squared goodness of fit test, taking a look at the alternative, which would be that the distribution is not as stated. Now, here's the one big thing. There's going to be some given distribution for you. Again, this is called a chi-squared goodness of fit test, but you might also see it as GOF. Three conditions for this. The first one's very uh, familiar to us, and it's random, right? Let's go ahead and clean that up a little bit. The first one has always been random. The next two deal with sample size. Is the sample big enough? So we want to make sure all expected values are greater than 1. And if there is a small expected value, we want to make sure that no more than about 1 out of every 5 or 20%, no more than 20% of expected values are less than 5. The one nice thing, kind of a catch-all for us, if all of our expected values are greater than 5, then we could go ahead and just state that as opposed to conditions 2 and 3. The way that a chi-squared distribution works and the way that test statistic works is you're going to take the observed values, you're going to subtract the expected values, and here's where the squaring comes in, because we want to square that over the expected. And what you're going to do is you're going to sum up all those different values. Oh, excuse me. And the reason we're squaring that is to keep it positive. As we sum these things together, right, we have a summation. So there's going to be this observed minus expected squared over expected. And then there's going to be another set of observed minus expected squared over expected. On and on it would go, right? So again, think about the M&M's example maybe. There'd be an observed number of reds versus an expected number of reds. And you'd add to that the observed number of greens minus the expected number of greens squared over the expected, so on and so forth. So you have a lot of different colors in that one bag, and we can put them all together. So the power behind a goodness of fit test is really it allows us to compare more than 2 distributions all at once. So, quick example, 2 traits have been widely studied in tomato plants and leaf type. So as people are doing these different crossbreedings of tomato plants, they end up typically with this distribution. So about 56% will be the tall plant with the cut leaf. About 19% will be tall, but with this potato-shaped leaf. About 19% will be shorter, the dwarf height with cut leaves. And then the least common uh, crossbreed uh, result would be the dwarf plant with potato-shaped leaves. So let's say that we decided we were going to do 1,611 different crossbreeds, and these are the results we get. We get 926 tall plants with cut leaves. How close is that to what we would expect? So what we would expect out of the 1,611, we'd expect 56.25% of those to be um, the tall cut plants, or about 906. So we got about 20 more than we would expect. If you keep doing that through, we should have seen about 302 tall potato leaf tomato plants. Well, we got a few less. Same thing here, right? So again, this is out of the 1,611. We'd expect about 19% of them. Kind of tough to see them on the end of the, but you can see the value there. Oh, for whatever reason, it's decided to erase my 302. And then we'd expect about 6% or about 100. So we got 104. So a chi-square goodness of fit test, what that's going to allow us to do is we're going to be able to take a look and see, well, are any of these far enough apart that we would start to think, well, maybe our experiment wasn't set up right. So first thing we want to take a look at, one, let's go ahead and note our degrees of freedom. There are 4 categories, so we'll subtract 1. That's 3 degrees of freedom. Our null hypothesis is that the distribution of tomato plants um, that we crossbred is the same as stated proportions. Trouble spelling. And then the alternative would be that the distributions of the plants we crossbred is not the same as stated. So we'll take a quick look at the conditions here. Randomness was not given to us, so we'll just have to go ahead and assume that we had a random sample. So that'll be not given, so we'll have to assume that things are random. And then you can see there, if you look down the expected values, 906, 302, 302, 100. So all expected values are greater than 5. So really what that tells us is our sample was big enough that we can go ahead and run this test with some confidence. That we feel good about running that test because it was a big enough sample. So from there, our chi-squared test statistic. So this is probably the most cumbersome part of the whole process. We have 926 minus 906.19 squared, observed minus expected, over expected. There's the first one. Plus, we had 288 observed minus 302.06 squared over 302.06. And we're going to do this for all of these. Part of it just to kind of prove that we know exactly how to set this test up. We know what's getting plugged in where. We also know what is associated with, which expected value is linked to which observed value. So there's the setup in terms of the formula, and it's at this point that we can kind of let the calculator take over. So if we were to run a goodness of fit test, we get a chi-squared value of 1.468. So what that really looks like, if we're on that distribution, somewhere along the way, here's 1.468, and it would be shading up. So if you don't have the TI-80 4 or above, if you have a TI-83, you're going to have to go to the chi-squared CDF, and then your lower bound is 1.468, your upper bound is infinity, and you have 3 degrees of freedom, and that'll give you a p-value that equals 0.690. So a pretty big p-value. So it looks like at any reasonable alpha level that we are above that, and so we'd fail to reject. And it looks like our distribution is right in line with what is expected. So go ahead and jot that sentence down there at the end, and you'll be good to go.